Alright, this is my operating systems project for CPU scheduling algorithms. So I use C++ to implement three different scheduling algorithms: first come, first serve, shortest remaining time first, and a multi-level feedback queue scheduler. Alright, so there are three main files: the scheduler, the workload, and the simulator. The scheduler has the code for the specific scheduling algorithms. The workload is what creates the processes in the code itself and reading it from a CSV. And the simulator is the shared, it's reading the processes in order and iterating over each one. Also, I created a lightweight metrics calculator, which just takes the averages of all of the turnaround, wait times, etc. The simplest algorithm that I implemented was first come, first serve, which is basically just setting the tasks to execute in the order that they arrived. The next algorithm I implemented was the shortest remaining time first algorithm. This basically runs the process with the least time to finish until there is another process with even less time than the current time. And it does this until all of the tasks are finished, effectively giving priority to the task with the least amount of time. All right, so the final and most complicated algorithm was a multi-level feedback queue. So I used three ready queues with quantums of 3, 23, and 65. And so these numbers are the time slices for each queue. So when a process runs for the allocated time slot for that queue, it's demoted to the next one. And then the next task in Q1 is ran for that quantum. And an additional modification I made to this is I added aging thresholds and boost intervals, where the aging threshold of 20 ticks basically has any process that is in the second or third queue waiting for more than 20 ticks without getting any CPU time is promoted up one level. So Q3 to Q2 or Q2 to Q1. And the boost interval is similar, but it, instead of based on the process, it's 80 ticks of system time and all jobs are reset to the base quantum of Q1. A process is going to arrive in the first queue. It's going to try to execute for 3 ticks, and it either finishes or it gets demoted to Q2. And then other processes will do the same thing, moving around in the queues, and the boost interval and aging threshold will act on all of the processes that are waiting for 20 ticks. So say this one waits for 20 ticks, it'll get demoted to Q1 again. But if it's not quite 20 ticks, it will finish the next time it comes to the second queue. And this will continue, the process of demoting, aging, and getting CPU time until all the tasks are complete. All right, and this is an example of a workload. You have ID, arrival, burst. All right, so the first graph is a histogram of counts versus wait times. And so each one of the algorithms has a very distinct graph, right? So the first come, first serve is very uniformly distributed, which makes sense for the first come, first serve because the waiting time is not dependent on any other factor versus when it was scheduled and what process is already running. And then for the shortest remaining time first, you can see a left peak, which basically shows that the processes are scheduled and they're ran, and then as soon as another one is waiting to be run with a lesser time to finish, it's instantly queued, thus reducing its wait time. You exponentially reduce the amount of tasks that have time to wait doing this, and that's where the quick decay comes from. And for the multi-level feedback queue, you can see it's not quite a pure right tail, but there is that idea there with the right tail, but there's also a decent amount of mass, like pseudo normally distributed, with the addition of the right tail, which comes from um, either smaller tasks or using the techniques like boost intervals and aging thresholds, which can effectively give processes that would be in lower queues more time to run within the smaller ones, reducing their wait time. And the really, like, the peak at the end shows starvation because these tasks are going to be in higher queues more often than not, and they're going to be waiting for a very long time until they're completely done executing. All right, so the next graph is the scatter plot of arrival versus exit time by algorithm. So the first algorithm, the first come, first serve, you can see that it's a positive linear curve. And this basically just means that any job's exit time is the arrival plus the sum of all previous processes that have finished executing, which is to be expected because it's a first come, first serve. An item enters, it exits, the next one enters, and it exits sequentially. Um, so the next algorithm was the shortest remaining time first, where you can see a line very close to the x-axis and then like a high distribution of points close to that, and they disperse as they go, which is very similar to the histogram showing the left tail of processes with a low waiting time because they keep getting pushed. The task with less time becomes like fewer and fewer as more time continues because it's going from this one to the next one as soon as the time is less, and it just keeps doing the cycle, like exponentially decreasing the amount, and that's why it fades really close to the top. And finally we have the multi-level feedback queue. Has all these like banding and everything. So the banding is really caused because of the different quantum, the 3, 23, and 65, the boost interval, and then the aging threshold. So what each one of these does is it effectively creates, for each pattern that it happens, so you have your 3, your 23, your 65, and then the boost of 20, or the aging of 20 and the boost of 80. All of these will kind of create like almost like a wave pattern, like that results in, and it almost creates a new baseline with each iteration of the global boost and aging thresholds. All right, so the next graph is the average turnaround, waiting, and response times between the different algorithms. So basically, what each of these means is that the first come, first serve has universal, almost poor service, like high wait, high turnaround, high response. MLFQ has poor waiting and turnaround, but it has very good response rates, only a fraction of the other ones. And then the shortest remaining time first has a very good balance between the waiting, turnaround, and response rates.